everyone, today we are going to continue on with our reinforcement learning journey, and that will be with SARSA. So up till now, you should feel comfortable with everything up to the Monte Carlo methods. We're going to do a quick recap of it today, but SARSA and the next model, Q-learning, are going to be much more practical ways of solving environments in model-free situations. So again, as a recap, the model-free part of solving a model is solving an environment is we don't have the model available to us. We don't have the MDP that describes the environment to us. And so the only way to solve an environment, to figure out what's the best action I should take in every single situation or in every single state, the only way to figure that out is by interacting with the environment. But this interacting with the environment actually has a couple of limitations, and that's what we're going to talk about today. So again, Monte Carlo was our first initial method of solving this. Monte Carlo is essentially, well, my goal is I want to compute what is my expected future reward given some state action pair, right? Or in this case, we're looking at just the values, so just the states, but either way, what is my expected future reward? As in, if I'm in the state and if I happen to take this specific action, what kind of reward do I expect to get in the future? That's the main thing that we're trying to solve for, because in the end, what we want to do is take the action that maximizes my future expected rewards. And so in the Monte Carlo method, and this is standard Monte Carlo, let's just go ahead and play the game a bunch, because I don't know anything about the environment. I don't know where the fires are. I don't know where the treasure chest is. I don't know what's good. I don't know what's bad. So let's just play the game a bunch, run a bunch of simulations, interacting with this environment. And once I interact with this environment, I collect some experiences known as trajectories. We'll talk about this again in just a little bit here, but we can take that accumulated experience, average up my computed future rewards, so I can go ahead and compute that ahead of time, compute them for every single game, and then average them together. And that gives me my expected future reward, at least an estimate of that expected future reward. And so the standard Monte Carlo method, again, is play the game, go ahead and average your results together using a standard averaging formula. Your expected future rewards for K games is just simply the average of the actual future rewards you got for those K different games you played. So nothing too crazy here. Now, the problem with this Monte Carlo method is it requires you to actually play the game. In this case, there's this 8, but you could have maybe 5,000 games or 10,000 games or millions of games. And the main issue is that every time you play a game, you need to store all of this information in memory, right? So you need to go ahead and store all this information, because in the end, what we need to do is take all of the trajectories from all of the different games, compute our returns, and then average those returns together. So this is a relatively memory intensive process because it will scale with the number of games you play and of course the size of the environment that you're in. So this method on its own is not really all that practical. So instead, we leverage something known as online averaging or online Monte Carlo. So this is the second part of that Monte Carlo video from last time, where instead of just storing everything and then averaging at the end, why not use an online averaging algorithm or formula, right? Nothing fancy. So you can look up online averaging. There's nothing very fancy about it. It just allows you to take the average up to, in this case, the 8th step. So instead of having to store all 8 iterations, all 8 games, and then averaging after the fact, I can just play a game and get my average up to the first game. Play another game, get the average to the second game. Play the third game, get the average to the third game, ... And so this means after I play one game at a time, I can get my average up to that game. So in this case, I'll get my average of all 8 games, but I only need to store the information of the game I'm currently playing. I don't need to store everything in memory. So that's a huge time saver there. A lot of memory saved there. And the online averaging formula look like this, right? So this is not exactly that online averaging formula. If you remember, we said that our QK plus 1, so my updated estimate of my expected return for some state action pair, is my current estimate plus some learning rate. In this case, we're using the learning rate of alpha t because that just seems to work better. But in standard form of a online averaging, this alpha t would actually be 1 over k plus 1, right? 1 over k plus 1 would be the factor here. But we can use a learning rate method instead because that's totally fine, as 1 over k plus 1 as k increases, as the number of games increase, then 1 over k plus 1 will decrease. So as long as you have some learning rate that's kind of decreasing over time, like an exponential decay or something like that, you'll be good to go. So we can use some learning rate parameter. And it's going to be alpha t times the return from the trajectory of the k plus 1th game. So this is the k plus 1th, the new game that I just played. I can get my trajectory, or I can get my returns from that trajectory from this specific game, and then just subtract my original QK value from there, right? So if you want to understand where this formula came from, go ahead and take a look at that previous video. We do a super quick derivation of the online Monte Carlo method. But notice here that all I need to compute my average of my expected return up to the k plus 1th game, all I need is my current estimate up to the kth game and my trajectory for the new k plus 1th game. I don't need to store the information of every single game because that's just too memory intensive. So this is online averaging. Now let's remind ourselves, what is exactly the trajectory? Every time we play a game, right, we go ahead and just interact with an environment until we hit the terminal state. In this case, the terminal state is, you fall into a fire, or in our ice game, you fall into like a hole in the ice, or you get to the treasure chest. So that means you've successfully completed the game. That's our standard trajectory. So every time we take a step in the game, as we're playing the game, we store at the first time step, I was at this state, I took this action, I got this reward, I ended up at this next state, and this is my terminal. Am I done or not? And you just go ahead and store this trajectory for that game. And you just repeat this over and over again for each individual game. Now, given these trajectories, right, given this trajectory, what I really have is this reward trajectory of, oh, at this state, if I took this action, I got this reward. And then at this state, at this action, I got this reward, ... And using that reward trajectory, we can go ahead and compute our future returns. So all of these formulas should feel familiar to you. Go ahead and take a look at the Bellman equation derivation and stuff like that if any of this doesn't feel comfortable for you. But the main idea is my expected reward, GT. So my expected future rewards to get at time step t is at the state that I was in at time t, I took some action. And that action produced an RT plus 1. And then I got my next reward, my next reward, my next reward. So I get a reward at every single future state that I end up in along the trajectory. And that means and the other thing we do is we weight it down. So we have some type of discount factor on the rewards, because we want to make sure that our model is able to balance current rewards versus future rewards. You probably want to put a little bit less emphasis on rewards that are far down the trajectory versus rewards that are very current. But that's the main idea. We have our actual reward from our trajectory. And that's the main thing that I want you to take away. Monte Carlo computes actual rewards from actual data from your trajectories. That's the main takeaway of Monte Carlo. Now, the problem is, to compute this reward trajectory, you need to go ahead and actually play a full game, which isn't that big of a deal here. Each game seems pretty short. Even though we've added some efficiency going from Monte Carlo, where you have to play all the games and then update your model, now we have online Monte Carlo where you can just update as you play every game. And this isn't a huge deal as long as your games are reasonably small. But what if you ended up with a game like this, a huge game, and even this is kind of small, but let's say you had a game with millions of states that you could be in, or billions of states that you could be in. The problem here is that if your game is large, that means every time we want to update the model, we need to play the game. But playing the game itself could be a very costly process. So we're going to go ahead and play the entire game, and then we update our model. Then we play a new entire game, and then we update the model. And then we play a new entire game, and we update the model. Again, we're just going to be repeating exactly what we had here, right? We're going to play a game and then update our model. We're going to play the game, update the model. Play the game, update the model. In this case, updating the Q values, right? Updating the Q values at every single iteration. But every iteration requires us to play a full trajectory, a full game, or in most cases, it'll be called an episode, completing a full episode, completing a full game. And then you go ahead and update the model, update your Q values using the following online Monte Carlo formula. So again, not a huge deal breaker unless your games become large. And in this situation, it becomes prohibitive because you can no longer efficiently train your models because every game just takes way too long. And so to solve this, we move into a new class of reinforcement learning models, and this falls under something called TD learning, or temporal difference learning. So TD learning, this formula should look identical to what we just looked at. So if we again look here, our QK plus 1, or basically our new estimate for the Q value, is the old estimate plus alpha times the difference between my return from the trajectory of the K plus 1th game and my current estimate, right? That's my initial formula that we had from the online Monte Carlo. Well, what if we treat it like this? So again, our Q value, our new Q value, will be the old Q value plus the alpha learning rate times some TD target, the temporal difference target, minus my current estimate. So it looks identical to before, nothing new. But what is this TD target? And what this TD target is depends a lot on what is the problem you're trying to solve. In the case of Monte Carlo, TD target was the true trajectory data. So you had to actually compute. You first need to get the entire trajectory, the true trajectory, and then go ahead and do your weighted sum, right? Exponentially weighted sum of the reward trajectory, right? Get all the rewards, add them together, and that gives you your true TD target from true data. So obviously Monte Carlo's preferable, gives you nice stable estimates of what those rewards look like. But on the other hand, you end up with this issue of, wait, I actually need to play the entire game before I can even do any of this stuff because I need that full trajectory. And so that's what slows it down. In another method, the one we'll be looking at today is SARSA, which is an on-policy method, which we'll talk about in just a second. SARSA is a TD learning method. TD learning allows us to learn at every single step. Instead of having to play a full game, so instead of having to play the full trajectory and then update our estimates, we can just take one step in the game, update our estimates, take another step in the game, update our estimates, take another step in the game, update our estimates. So we're updating our estimates as we're playing the game rather than once we've completed the game. And that's the key idea. Now, obviously, this allows for quicker learning because we can interact with large environments without having to actually complete playing an entire large environment until we do an update. So this is very nice. But how does this work out? Let's take a look. This here is in Monte Carlo, we have a reward, so our current reward, plus discounted future rewards. But what exactly is the discounted future rewards? Isn't that just our Q values, right? The Q value is our future rewards. It's an estimate of what those future rewards are. So instead of grabbing my future rewards from true trajectory data, which is this, what if I just use my current estimate of the future rewards from my Q values? Because that's exactly what it's supposed to be. So basically, the idea is that I'm at some state S and I took some action A. And being at some state S and action A produced some reward RT plus 1. But when I took action A, I ended up at some new state S prime. And then at that S prime, I took an action A prime. That's the key idea. So again, remember, we are going down this reward trajectory. I'm at some state S, I took some action A, and I got some reward, RT plus 1 in this case. And then this action sent me to this new state, S prime. And then at S prime, I took my new action, A prime, so on and so forth. And so all I'm saying is, instead of using the true reward trajectory, why not just use my current Q value estimate, which is also supposed to be my future rewards, instead? And this is known as bootstrapping. So bootstrapping is a common method used in statistics, right? And the idea is we want to estimate something by using another estimate, which obviously doesn't sound like the most stable way of doing it, but it allows for faster learning because we don't need the full trajectory. And it also allows us to work with partial episodes, and it also allows us to be memory efficient because we don't really care about the entire trajectory, just the part that we're looking at. So the main takeaway here should be, in TD learning, instead of waiting for the future to unfold, going through the full trajectory like Monte Carlo, we just use a current guess of the Q values as our TD target. So TD learning uses bootstrapping because it updates Q values using an estimate of the Q values. So it's kind of updating with its own estimate of itself rather than using actual returns like Monte Carlo. So of course, this leads to more challenging convergence issues. It also requires better exploration versus exploitation balancing, stuff like that. But for the most part, this is still a more practical way of learning because you don't need to play a full game to update your model. And so that's the main idea. So SARSA is the method we'll be looking at today, and it is an on-policy method. And again, the main idea is instead of computing a true estimate from true trajectory data, why not just use the current estimate of this next state, next action pair as our best guess of what this should be. So we're using this estimate to estimate this true data. And that's essentially the main change between Monte-Carlo and SARSA. And now SARSA, like I mentioned, is an on-policy algorithm. We'll also talk about off-policy, that's Q-learning in the next video. But today let's just talk about on-policy. And on-policy is very simple. The idea is that we want to update the policy based on the action actually taken in the next state. So the main idea is that I have here, I was at some state, I took some action. And then I ended up at some next state and I actually took this action. I have that in my trajectory information, right? So that information is available to me because I have the trajectory. I know what action I took in the next state, which means let's just go ahead and use the Q value estimate of the next state and the next action actually taken at that next state. So this is called on policy because we update the policy based on the action taken in the next state following exactly the same policy. So we're just following the same rules of what we have here. Off policy has its own benefits. We'll look at Q-learning later. But for now, let's go ahead and just implement SARSA. It'll be very simple. So what we're going to need is essentially to follow this formula, this TD target. And for SARSA, we have the formula for the TD target. It's the reward we got plus a discounted future rewards, where the Q values is our estimate of the future rewards. And we're essentially using an estimate to solve for itself, which is what makes it a bootstrapping method. So to implement SARSA, we're going to need a couple of things. So import numpy as np, import gymnasium as gym, standard imports, and we're going to implement two different things here. First, epsilon greedy. Epsilon greedy. So like I mentioned, these methods like SARSA and Q-learning require more random sampling, because if you're going to be playing with the environment and trying to make some kind of an estimate about it at every single state, every single step as you're playing the game, then you need to be a little bit more random to explore the environment more. In Monte-Carlo, this was kind of handled because you just played the game a bunch and then averaged it up after the fact. But if you're going to be making an update to your Q values at every single state as you're playing the game, then we should be a little bit more random about how we go to next states and stuff like that. So the main idea is, do we want to follow the policy, which tells us what action should we take at a state, or do we want to go ahead and just take a random action at a specific state? So let's go ahead and epsilon, well, I can't spell that, epsilon, there we go, and our environment. So if np.random.ran less than epsilon, so epsilon, we can set it to some proportion, but let's say if it was 50 or 0.5, that means 50% of the time we'll take a random action and 50% of the time we'll follow the policy. So if it's a random action, then we're going to return env.action space.sample, right? So we're going to go ahead and just sample a random action to take at this specific state. No problem there. Otherwise, if we don't want to take a random action and actually follow our own policy, then we're going to say np.argmax, return np.argmax, and we're going to do Q state. Take the action that has the maximum Q value at that specific state. And so that's our epsilon greedy policy right there, right? Or learning method, essentially. So now we can go ahead and implement SARSA. We need the environment, num episodes. Let's say we want to play 25,000 games. Alpha equals 0.1. We're going to, and that's just a constant learning rate for now. Of course, we could have a learning rate scheduler or something like that. Let's just keep it simple today. Gamma is 0.99. That's our discount factor. And then epsilon is 0.1. So that we're going to say that 10% of the time, go ahead and take a random action. And 90% of the time, let's go ahead and follow the follow our policy. We could also write a scheduler for epsilon, where initially when we're just playing the game, go ahead and take lots of random actions so we can explore the environment. And when we are kind of more along and we've learned a little bit, go ahead and start following the policy more. There's lots of options here, but we're just going to do something very simple today because our environment is pretty easy. So our Q values, just like normal, np.zeros, we're going to just initialize them as zeros. So env.observation space.n and then env.action space.n. So this is our Q table of what are all the states we can be in and what are all the actions that we can possibly take. And so that's all we need right there. And now that we have our Q values, which are just initialized as 0, we're going to update these Q values at every single state as we're playing the game, or every single step as we're playing the game. Let's go ahead and start a game. So for episode in range num episodes, so we still have to play many, many games, but we can update at every single step along each game rather than waiting for a game to end and then updating. So that's the main thing. Let's go ahead and grab a state, env.reset, and then we're going to go ahead and select an action. So we're going to do action is our epsilon greedy, and it's going to be, here's my current Q values. Everything's just 0, but that's fine. Here's the current state that I'm in. Here's the epsilon that I want to use, 10%, and here's the environment that I'll be interacting with. And then what we're going to do is, once we've selected an action, it's time to actually play the game. So we've started the game, we've selected an action, we can now go ahead and start. So we're going to do done equals false, and we're going to do while not done, so until the game is over. We could also add a hard bound of saying you can only play up to like 50 steps, and anything more than that is too much. But again, for now, this is fine. Let's go ahead and take a step in this game. So next state, the reward, done, and then we don't really care about these things, is env.step action. So I have now taken an action inside my game, and that's produced my next state, S prime. I get my reward for taking that action, and I can get, is the game over or not, right? So that will end this loop if it is over. And then what is my next action? And this is again epsilon greedy, Q, next state, epsilon env. So what I'm doing here is sampling my next action that I'm going to take in this game. So that would be this right here. So let's go back here. So I started at a state. We started at this state, and we selected this action to take using our epsilon greedy method. So we started at this state, and we took this action, or we selected this action. We then actually take the action that takes us to the next state, and then we sample a new action to take at that state. And we again use the epsilon greedy method of either randomly select an action or go ahead and select from our Q table of what the best action should be. So that's our next action. And lastly, we now can use our update rule for a state action pair, right? Let's just look at the formula. Our Q value for a state action pair is the existing value minus our learning rate times the TD target minus the existing estimate, right? So let's just go ahead and do that. And this is our TD target for SARSA. It's the reward we got plus discounted future rewards at that next state, next action pair. And that's what makes it on policy. So we're going to do the Q state action is going to be Q state action again, plus alpha times, it'll be the reward that we got at the next state. So that's going to be this one right here. We took an action, we got a new reward for RT plus 1, so future reward. And then we're going to do a discounted future rewards. So Q, and it's going to be next state, and the actual next action that we're going to be taking. And that's the main idea for our TD target. So that's my TD target right here. And then we take the TD target and we subtract from it QSA. So again, my current estimate, QSA. So we can go ahead and do that. So it's reward plus, reward plus gamma times all of this minus Q state action. So that's the current state, current action, right? The first set that I did. And now that I have all of that ready to go, I can set my new, or basically my state in action now for this next iteration will be the next state, next action. And we just keep repeating this until we've played all the games, and we can return Q. We could also add a convergence policy in here where if Q stops changing, then go ahead and just break the loop. But for now, this is all fine. So again, the main takeaway should be that in SARSA, we iterate our Q values at every single step of the game. And our formula is basically our new Q value is the existing Q value, and we update it in the direction of our future expected reward. So that's the reward plus discounted reward, what I can expect to get in the future. We're using our current Q values to estimate the future Q values. And that's the main idea here and what makes it bootstrapping. We're using the Q values to also estimate our Q values, where in Monte Carlo, we would actually compute what that reward would have been or the return would have been from an actual trajectory, from actual data. But notice there's no trajectories here. There's no sampling of a trajectory. There's nothing happening. We're just updating our Q values at every single iteration using this formulation, using our TD target here. So that's what makes a temporal difference learning. A little bit different, but pretty interesting that it works out pretty well. env is then gym.make frozen lake v1, and then is slippery equals true, right? We make a slippery environment, stochastic environment, and so our Q SARSA is going to be equal to just the SARSA on this environment, right? That's the environment that we're trying to solve. Everything else can be left alone. And so our policy, so if we do our policy is what action should we take at every state? Well, that's going to be np.argmax Q SARSA. And then we'll do axis equals -1. So for every single, remember, we have a matrix of Q values of number of states by the number of actions. We want to find the max Q value, basically highest action Q value, highest Q value for each action for every single state. And so that's going to be find the maximum Q value along the action dimension, giving us the best action at each state. And so now we can take a look at our policy. Let's go ahead and take a little bit of time. There we go. So that's the policy that we got. And we can go ahead and just use our test policy function from before. Again, if you haven't seen this, we've implemented this a couple times already, but the idea is just go ahead and play the games. And then if you actually get a reward of 1, which is all the frozen lake environment gets, you get a reward of 1 if you reach the goal. Otherwise, it's 0 and it's fine. Then you get your thing. And we can see here we have an 81% success rate on a stochastic environment using our policy derived from a SARSA model. So this is the main idea behind our TD learning. TD learning essentially fixes one of the main limitations of Monte Carlo, where instead of having to actually play an entire game, instead of having to actually interact with the environment, play a whole game, do an average, whether the average be kind of this dumb averaging or an online averaging method like this one, instead of having to actually compute this G, which is pretty expensive because you might have to play these long games and then do it afterwards, it allows us to use our current estimate of Q value as a drop-in for the true values that we would have gotten from trajectory data. And it does this via bootstrapping, right? So this method of using an estimate to estimate itself is known as bootstrapping. And again, this is an on-policy method because we're using the Q value estimate of the future state and future action that we actually took. So it's following the same policy because we're using the future state and the future action that we actually took. In the next video, we'll be looking at Q learning, which is an off-policy method. So I will see y'all in the next one.